this is a brief introduction on impact and Google Earth Engine API and facilities that have been used in support to the Sardinia land cover project, so a collaborative activity between the Department of Chemical and Geological Science of the University of Cagliari and the Regione Autonoma della Sardegna. So the structure of this presentation is going to be like a brief introduction on the Sardinia land cover project with an overview of Impact Toolbox, an overview of the key features, and some case studies, like in this case, burnt areas mapping, using Sentinel-2 data and Google Earth Engine platform for querying data and also downloading data. So requirements, actually there are no requirements, but however, okay, it would be nice if you have the Impact Toolbox installed on your PC, maybe not right now, but if you want to do meanwhile, this is fine. The tool can be downloaded from the European Commission webpage called FOROBS, Forest Observation.JRC Europa, and so on. If you have a Google Earth Engine account, you can benefit also from some features available in Impact Toolbox, and you can also download pre and post fire event imagery directly from Google or from the drive that where I've put some reference images as well. As I said, I want to make this presentation more interactive and productive, so feel free to interrupt me and raise your questions and suggestions. So, as just said, the Sardinia Land Cover Project is a project in collaboration between the University of Cagliari and Regione Autonoma della Sardegna, with the aim of producing a Sardinia land cover cartography and also monitoring system of irrigated areas using remote sensing data. Remote sensing data, namely Sentinel-2, Sentinel-1, and why not ancillary data, so existing maps, existing vector and raster maps that are available from previous studies. How the project is structured, or it has been structured right now in this preliminary phase of data collection and data processing. So via the Google Earth Engine platform, we collect a lot of Sentinel-2 data, multispectral data, actually, from near red, near green, red, RGB, near green, blue, and near red, near, sorry guys, red, green, blue, near infrared, sphere 1, sphere 2. Masking for cloud, because of course cloud for visible, for the optical data, it's always an issue. Creating monthly composite, most likely a cloud-free composite, and also extracting several indices like NDVI, NDWI, phenology-based classification, and so on. Regarding the Sentinel-1, we collect data, we create some composite using the V and VH band, and extracting some ancillary or extracting some extra data like built up surfaces and so on. We also have a good bunch of ancillary data regarding land use, previous land use mapping project, orthophotos, and so on. In Impact, what we have done, again, we can rebuild some ad hoc indices. We will see during the presentation how to do that, and also applying some image segmentation, image classification, in order to better refine and validate the land cover classification, and at the same time provide a quality check and accuracy assessment. So this is in brief the context of the framework under which this project, this presentation, this initiative has been done, where Impact plays a role in this presentation regarding the burnt areas mapping. So in brief, what Impact is a portable GIS application. It's a free and open source, and provides a balanced mix of image processing, remote sensing, editing features, and photo interpretation tools. To do what? To do a quick data visualization, mapping, and editing. And why not also performing some ground truth collections? Okay, we are not speaking about professional tools or very sophisticated tools, for instance, developed by FAO, like Collect Earth and so on. But this is a really handy tool that it runs on your PC easily, and you can experimenting also some ground truthing using this application. Why using Impact? There are some common problematics, like different softwares, different environment, like switching between MV format or other GOT formats. So sometimes you have these proprietary formats that are difficult to deal with. So there are also some cost involvement. With Impact, we try to bypass this limitation, providing a free and open source software, easy to use. This is the key point. We have, every day we are using QGIS, but don't forget that the Impact, as I said at the beginning, was developed for capacity building. Capacity building in land cover mapping with the aim of helping those institutions in reporting about the land cover changes and the mission, specifically in forests. So having so many tools for a non-GIS expert, like in QGIS or ArcMap, was at the beginning too difficult. So we decided to build up this tool that was then easy to use without any installation, portable, so you can switch easily the platform where you are running, the PC where you are running the Impact, just leave it on a key or your external drive. And sometimes also working without internet connection, because in some remote places in the tropics, internet is a luxury. So that's why we thought, okay, let's go on this direction. And especially the tool is customizable, so you can develop your own pre-processing script, classification, segmentations, and so on. Okay, it works in Windows and in Macintosh. Recently, we have built it under a Docker, so you can run it in a native, let's say, format in Windows, but also on Mac or Unix using a Docker. It's a client-server application, so it's not a standard way of working for such a tool. So you have an engine that is your server with Apache, Tornado, and you have more info on the website, on the description of the tool. But this is the concept, is a web server, so running on your PC. So that means that you can also install on a server in your facilities, in your premises, and use it as a reference entry point for storing, visualizing audio data and processing, of course. Okay, in Macintosh or Linux, this is pretty much the same. But I don't want to go, let's say, too much in details, because the objective of this pre-conference course is mapping burnt areas with Impact Toolbox with hands-on the tool. So an interactive section on how to perform it. And okay, my objective is also to show you how quickly and how easy it will be, or it is, to map this kind of land burnt areas or land cover in general. So if you have some questions before jumping into the core of the presentation, feel free. Okay, no questions? Or please, from the Regia, if you see some comments in the chat, feel free to interrupt me as well. Okay, so the case study, July 21, a couple of months ago, big fire in Oristano area, west coast. We have seen so many news, also newspaper reporting about this fire. like Sardinia is burning, 20,000 hectares devastated, Italy receiving a lot of help and contribution to fight the Great Fire, and so on. So when I was discussing with the colleagues at the university, and also in a broader context within the European Commission, where the mapping of active fires and burned areas, it's quite robust, not only in Italy, but also in the whole tropical belt. So the first thing I thought was, okay, let's see the sources of information we have to map this fire. So we can go through, for instance, the NASA films, that is the platform that is reporting the active fire. That is a really, let's say, it's called a fast response. So it's you can see in a matter of few hours what is going on in terms of hot spots or of hot pixel in the map. And indeed, the cumulative number of fires between the 6th and 26th of July shows this red zone in the area. Luckily, we had also very nice and cloud-free images from Sentinel showing the extent of the burned areas at the 30th of July. But to go more in depth, how can we burn this mapping, the extent of the fire? In order to simplify your life, in the drive, in the link that you see in the presentation that will be shared, of course, I've put several subsets of the Sentinel-2 imagery that you can get either from the NASA website or the Google Earth Engine website, in order to speed up a little bit the processing also from your side once you are back to your office. So the first step is how to identify the most suitable Sentinel-2 imagery for this application. And indeed, you can use several tools. You can go to the ESA website. You can go to the Google Earth Engine website, to USGS, and retrieve any kind of data. But recently, what we have implemented in Impact Toolbox was the link with Google Earth Engine Python API. So it's very convenient. If you have a Google account, you can type it in Impact and use the Google Earth Engine time series application to query every place in the globe and visualize the availability of Landsat, or in this case, Sentinel-2 imagery. So during the presentation, let's see if I can jump to Impact Toolbox. Okay, do you still see my screen? I think so, because yeah, I can also see a chat. Okay, yeah, if you want to ask something, just put it in the chat. I will keep an eye from time to time. Okay, so the first objective is, how can I see which are the available images that are suitable for my analysis, which are the dates, if there are clouds and so on. So now I'm zooming in the area of interest, and by using the time series and adjusting the period I need, because I know that the fire occurs in July, so I jump to July 1st up to now, selecting Sentinel-2 data with a buffer of, let's say, 5 kilometers around the area of interest. So now when I zoom, when I click with the inquire cursor here, what you see, hopefully, it's a list of Sentinel-2 imagery showing the evolution over time of the fire. So I can see clearly that the 22nd of July, there was nothing in this area, but the 25th Okay, Sentinel has a repetition, has acquisition cycle of 5 days. So there might be a gap in between. So we don't know exactly when it happens. That's why I was also looking at the films, so the active fires data from NASA. But indeed, the first available image, Sentinel-2 image, about the 25th of July shows a tremendous burn scars. And then that is still visible here, the 5th of September. So by going on any other website, Google Earth Engine, or why not ESA website, we can directly go and pick up those dates, the pre-fire and the post-fire. The pre-fire can be the beginning of July, and the post can be end of July or eventually September, August. Okay, so now we jump in the data acquisition. Since the presentation is the link between Google Earth Engine and Impact, one way can be using a Google Earth Engine script to retrieve our data for a quick download. So you can go on this link that contains the code to the Google Earth Engine platform and selecting the area of interest here, the date selection. We know that it happens in this period, the cloud percentage in case, the band, the visualization band combination, and the export to drive. The export just shows, once it's done, the GeoTIFF file with a predefined band combination in your export drive. Similarly, you can do that via the Copernicus Open Access app. It's pretty much the same. You select the period, we know exactly which are the best images, and you can download. The difference is with the ESA, you download the raw data, so the zip file with every band in a JP2 format, that is this very high compressed file in JPEG version 2 format, JPEG 2000 format, that is not probably so convenient, while in Google Earth Engine, what you get is a layer stack GeoTIFF resample in 10 meters band. Okay, but never mind, because Impact has an application, as a module that takes all those images, raw data, zip, and does the layer stack for you, and also resampling and so on. So now the next step, once we got those data, it's okay, performing the layer stack, maybe clipping, subsetting, applying some classification, index extractions, and so on. And later on, image segmentation, maybe statistical extraction from different rasters, called zonal statistics, and visualizing the output. Why not in Google Earth Engine, in Google Earth, sorry, for 3D rendering, overlay, or KML, or placemark, and so on. Okay, if there are no questions so far, we can jump to the hands-on session. Okay, so in brief, the tool has a lot of options for processing, ingesting, clipping data. In the presentation, as you can see, I have a bunch of slides for each tool, like ingestion, clipping, adjusting the geolocation, mosaicing. I'm not covering all of them, like temporal or spatial mosaic, classification, reporting, emissions from deforestation and degradation. So those slides are all in the presentation, and okay, it will be accessible for any further analysis, and so you can go through easily. So I don't want to bother you showing all those tools, but just covering the key and essential steps that are involved in the mapping activity. So one key step is, of course, the ingestions of zip file or GeoTIFF. So Impact Toolbox comes as a directory in Windows or in Unix or Macintosh. It's yeah, again, it's a bunch of data containing some scripts, a tool to launch it in Windows, and a data folder. Data folder contains everything you need. You need to visualize, or you need to process, and so on. Don't forget that you can put in this directory GeoTIFF, TIFF files, shapefile, Esri shapefiles, and so on. And you also have some tools to convert data if needed. So coming back to the presentation here, to the Impact Toolbox, once we identify which are the images that we need, you can see here a module to ingest Landsat, Sentinel, and RapidEye, because those are the images that have been used so far. But don't forget, we can build up some extra modules for other applications as well. So now the idea is to ingest our Sentinel data. Ingesting is pretty much easy. So once we download our GeoTIFF zip, sorry, not GeoTIFF, but the zip archive containing our Sentinel data, it's enough to go on your drive where you download it, select them, confirm, and in batch, the tool is automatically ingesting band 2, that is the blue, green, red, near infrared corresponding to band 8, SWIR 1 and SWIR 2 corresponding to 11 and 12. So we want to keep a kind of similarity with what we have with Landsat, but this is just for, let's say, keeping a standard band combination that is the same compared to different sensors like Landsat, Sentinel, and so on, or RapidEye as well. Eventually, we can provide an area of interest. But what I want to do right now is to show you what's happened when you click this button. So it's pretty much easy. So the tool starts, and you will see in your directory here, this is the place where all your data are then visualized in Impact. You will see 2 directories containing the big image corresponding to what we have acquired. So this is the first image corresponding to the 5th of July, 2021. And this is the second folder containing the second image of the 30th of July. By switching on and off, we can overlay the two. Okay, now I'm zooming on this small, big fire, but small area, and overlaying again. So our objective now is to map the extent of these burned areas, but similarly can be done for the entire land cover or for any other topic in impacts. So coming back to the presentation, which is the second step. Once we have the images, I think a common task is to clip, to subset the image into a small portion that is more handy to be used. In this case, the tool is called image clipping. And if we go to the Impact Toolbox, it's right here in the second place in the processing panel list. So clipping an image is very easy. What we can do is to draw a rectangle and then saving the rectangle as a vector file, as an Esri shape file. And by doing this step, we will see the file automatically appearing in the data list. This is quite convenient because every file you show or every file you process, it automatically visualized in the platform. And another trick is that everything you do with a file, like renaming, copying, or deleting, it's physically done on your data directory. So this is quite convenient when you have a lot of data, you want to delete what you don't need, or you want to move some files in another folder called maybe trash and so on. So there is this kind of interaction between the file and the file system that is unique within the same let's say application. Of course, you can change a little bit the layout and so on. So once we have this area of interest, you can find the same in the Google Drive. So in the data set, in the bunch of data I'm sharing related to the presentation, you can already find a vector file called AIT file subset. So this is my reference for this presentation. So we are now looking at how to clip data in this area. It's pretty much simple. There is a tool called Clip Raster from Vector. We select the images that we want to clip. First the vector data, in this case can be the area of interest or the file subset. We confirm, and the images that we want to clip. That is, in our case, there are just two images, the pre-fire and the post-fire Sentinel data. Once we confirm, we can run it. Okay. By running this tool, I click run. Okay. What you can see here is the log monitor changing in color, saying, okay, before it was green, now it then came orange, and with red it says that something went wrong, maybe in the past, like in this example. And in the last option, you can also trace, oh, what's happened?
Dottor Simonetti, sono Barbara. Provi, esatto, a ricondividere lo schermo.
Yes.
Adesso si vede tutto.
Perfect. Yes, because I was, yeah. Okay, so in this case, you can see and you can trace what you have done in a kind of log monitor, saying that, okay, the image, the vector file I've used, the output file, the input raster data, and so on is all there. And going back to my panel, expanding the directory containing the Sentinel-2 data, I can see the subset with a prefix related to the vector data. I've done it simultaneously, so in one click I got two images, one for the post-fire and one for the pre-fire. Okay, so very easy. So few steps just to get a clip of the two images I want to interpret and map. So what's next? Okay, this is adjust the image to the location. This is not always needed, especially when we are dealing with a single sensor like Sentinel-2, even though sometimes there is half a pixel or 1 pixel shift, but ESA, it's going to improve a lot the geolocation accuracy. But indeed, we can also play with the geolocation in case we are comparing data from different sensors and there is maybe a mismatch of a few pixels, because this is exactly what we want to be sure of. So ensure a perfect geolocation. How to do that? It's enough to flicker between the two images. in order to understand if there is a good relation, a good match between them. So, and it seems so. In this case, the two Sentinel data are well geolocated, so no need. But don't forget that you have also this tool. Image mosaic in this case we don't need, and so on and so on. So I'm gonna jump now that we have the images, we are gonna jump to the next step. So ingesting data we did, everything goes into your impact data folder. In case you have some GeoTIFF files because you exported via the Google Earth Engine archive, or because you have your historical data, you have your own data, don't forget that you can always put those files into your impact data folder. Once they are there, can be automatically shown in the interface. So we draw an AOI, an area of interest, and we save as GeoTIFF, as a shapefile, sorry, in order to clip the GeoTIFF images that we ingested before. So what's next? Usually we try to perform, when I say we as a user, as the user dealing with the land cover mapping, I try to test the quality of some classification algorithm. Classification means automatic, supervised. Supervised is another story, but in this case it's automatic classification, k-means, or other applications if you are dealing with water, like the water dynamics tool that is based on indexes and so on. We are not covering this topic right now, but it's an option available in Impact. So classification, what does it mean? Means building clusters or classes corresponding to pixels that are spectrally similar in a number of categories that we are defining a priori, or that we get from the automatic classification. In this exercise, we are trying both. We can try the automatic classification or the k-means or any other classification that is performed also outside Impact Toolbox. I want to do a brief excursus on the automatic classification also linked with Google Earth Engine. This is not the topic of this presentation, but just to give you also the idea, the concept, to pass the concept that any kind of classification can be ingested in Impact, can be visualized and used for the objective. Okay, so classification done with random forest in QGIS or Google Earth Engine and so on. But this is a very brief excursus on Google Earth Engine processing power. So yes, Google Earth Engine has a public catalog containing tons and tons of data. This slide is a little bit old. It was done a couple of years ago, and at that time already 5 petabytes of data were available, accessible. The amount of data is increasing daily, especially with the ingestion of Sentinel-2 data once every 5 days, so on the same location. So imagine the size is growing exponentially. So with a specific interface in Google Earth Engine, you can process your data and you can also save the derived products on your drive. Just to give an idea of the classification algorithm I implemented in Impact, that it's publicly available also as a Google Earth Engine code. It's very basic. It's starting from an NDVI classification, adding some band combination, relation between bands and indices in order to split and to categorize the amount of pixels in input into some thematic thematic classes. I don't want to say land cover because, well, land cover is a little bit too optimistic, but let's say classes corresponding to image colors or colors extracted from the images. So what we can do in Impact is just a single date classification. Once you take your input Sentinel, Landsat, or whatever image, you can apply a classification of that single image. In Google Earth Engine, and so we get a status, we get a snap of the classes in this specific time and space. So if we can see, like in this case, some green classes, we can say that they are corresponding to this green vegetation, the bright or soil classes, and the clouds and shadows, but it is always linked to that specific time and space and image. The advantage of Google Earth Engine or any other cloud computing system is that we can apply and iterate this classification algorithm all over the collection within a specific time frame. It means that we can take every single image belonging to the same place or to the entire continent or region, and we can apply a classification and then having a sort of evolution of the classes. In Google Earth Engine, and you can see the publication here, you can also apply some conditions based on the phenology of this evolution of classes. So we jump from pixels to classes, thematic classes, where the definition of the phenology is much more simple. So this is the great advantage. So we can map deciduous vegetation, evergreen vegetation, where we can observe some constant in the classification and so on. So, okay, this is just to say, okay, in Impact, you can put any kind of classification, but of course, there are some limitations. Like I was processing years ago with a single process approach, one CPU approach, and so on, images over Nairobi. And in 2000, it was about 2014 when I did this exercise, so many years ago. And in order to process all those 14 Landsat images in Impact with only one CPU, just to be, let's say, optimistic, I took 2 hours. In Google Earth Engine, it took 0.5 minutes, so 30 seconds to get the classification of those 14 Landsat. Imagine you don't have to download data, to pre-process data. Everything is in Google Earth Engine and is available for any kind of processing, including the classification. But okay, so how to perform the classification? It's in Impact, it's quite easy if you don't have any other sources. So it's enough to explore the automatic classification and this tool. So this automatic classification is reproducing exactly the code developed for Landsat and Sentinel that is available in the Google Earth Engine link that I provided in the slide. So you can test how this classification works. So it's enough to select the image. You can select both images, can be the full or the subset, confirm, and you can run the button, push the run button. Once it's done, and for this subset, it's very fast, it takes just a few seconds, you can see the result in your drive. Okay. This is the classification of the pre-fire image. The green classes correspond to the vegetation, then the soil, and some, okay, violet classes to dark soil, and so on. So similarly, I can do that for the post-fire event. I'm going to move the image on top and removing the pre-fire image. And this is what I can get from the automatic classification. So I can see there are a lot of gaps in the mapping of those burned areas. But okay, it doesn't matter because the automatic classification is not the only tool we have. We can explore a little bit more in just few clicks. So if there are questions, or if you want to propose like approaches, or you want to propose something, we can explore, we can interact. So feel free to raise your hand. Okay, so if there are no questions, so in order to follow the original workflow, we went through the automatic classification. This is something that just by pushing one button you can have in Impact and in Google Earth Engine as well. We have a raster data, but as we have seen, the automatic classification is not enough to map correctly all those areas we are gonna look. I can see a hand raised. Tommaso Rusa, please.
Yes, sorry if I ask a question. It's only curiosity. Is there any possibility to implement some algorithm in Impact? For example, not only write new ones, but for example, I'm thinking about SagaGIS tool environment that have a very strong algorithm. If there is any possibility to try to take this algorithm and put into Impact in order to have a more powerful tool. Yeah, it's the question. I hope you have understand. Thank you so much for all.
Yeah, thanks so much for the question. This is yeah, pretty much pertinent, and I can say yes, this is possible because Impact it's written in Python. All the engine behind is in Python, and the interface is in JavaScript, so XJS. So there is no nothing is hidden, I would say. And in order to give you a live demonstration, I'm not gonna implement right now the code, but I just want to show you the structure of the tool and to give an overview. So you see there is a directory called libs containing all the libraries for the interface, and a directory called tools. So when I jump into the classification tool, you can write your own Python script, you can copy it from Saga if it's an open source and so on, and you can put it there. It's enough then to create a link with the interface in like another module here with a button, and reusing the template for the processing window in order to call your own Python code. This is pretty much convenient. We are limited as a let's say decision for the capacity building approach to limit a little bit the number of tools in order to keep just the extremely necessary tool for the mapping activity. But of course, you can also run the classification in Saga, QGIS, you can import modules, Google, whatever you want, and copy the file in Impact. I hope I answered your questions. And yeah.
Yes, perfectly. Thank you so much. It's very nice work. So thank you so much. I just only have another one, then I stop. I'm sorry. You mentioned about the Google Earth Engine, and there is a way to link it directly if we have an account, our account, in order to call the image collection and so on.
Yes, yes, this is totally doable. Actually, what I've shown before, just clicking on this Google Earth Engine tool, it's using my own account and using the Google Earth Engine API in Python. So when I click on any location, I can get the information of my Sentinel-2 data, but similarly, the entire time series of, in this case, Landsat or Sentinel data for that specific location. I can change the band combination, the stretch, the satellite, and so on, but everything is based on some Python code developed using the Google Earth Engine code. If you want, you can put in the Google Earth Engine directory any kind of tools you are writing using the API of Google in Python. So yes, also downloading data can be totally possible. Maybe adding an extra function with a right-click download image, and you get it directly. But yes, you can do that.
Okay, thank you so much.
Welcome. And of course, if you have some technical issues or questions, how to integrate your own code, don't forget to write in the chat, to contact me even later on, and we can see how we can support also this implementation. The tool, I remember, it's free, open source, and every changes are then visible thanks to an automatic update, dissemination update based on Git repository to the entire community. So if we develop some extra modules, everybody can benefit from it, unless you don't want to distribute. This is another story. Okay, so we have seen automatic classification. If there are no, okay, yes, the slides will be available. Yeah, okay, so we answered this question. So we can go ahead. Our objective is to map the extent of this burned area. Okay, that happened in July 2021 in Oristano. Okay, so we tried the automatic classification, but in order to be, let's say, in line with the tradition, there is one index that is supposed to map correctly the extent of the burned areas. That is the normalized burned ratio called NBR. The NBR, let's jump into the slide. Yes, so presentation. In order to do this kind of mapping using indices, in Impact, there is a tool within the analysis and announcement here in this section with this color, shining color icon. That is an index builder. It's very easy. It takes two bands and applies the formula used for the NDVI. So B1 minus B2 divided by the sum of those bands. So just using this simple formula and changing the band, the input bands, we can build NDVI, NDWI for the water index, the snow index, the soil index, and many others. So it's up to the user now to see how to interact with the band selection to build the, in this case, the NBR. So the NBR, the normalized burn ratio, uses as band 1 the near and SWIR 2. So near and SWIR 2. Let's jump into Impact and try to calculate the NBR. So it's pretty much easy. So we take, oh, sorry, I took the linear spectral mixing. That is another story. So here, the NBR, so we select the two images. So it's very easy. So the AIT, the first image, the second image belonging to the post-fire event. You can also check with the name, some information, and so on, the bands combination, the bands. So we have 6 bands, our default application. And as we said in the presentation, for the NBR, we are gonna take the near and the SWIR 2. Near and SWIR 2. So our input image takes by default red, green, blue, green, red, near, SWIR 1, SWIR 2. So we are gonna use band 1, 2, 3, 4, 5, and 6. 4 and 6. 4 and 6. And even if you do a mistake, doesn't matter. So NBR test 1, how to see if we are doing a mistake in the band selection, if we don't remember which are the sentinel band. So we expect that the output of this NBR test 1 gives, I push the run button, is running in background. We see one process running, finished. So pretty much fast. So how to see the correctness of this index? So we expect values within the burned areas of very high values. So we put this image on top. We show the post-fire event here, and we see that is the opposite. So in this case, we did a mistake by building the index using a swapped, let's say, band order. No problem. We are just clicking on the tool again, and we swap like 6 and 4. Okay, and I call it test 2. You see, with just few clicks, I built 2 times the same index. I can also override the output in order to be sure, but for this exercise, I did it on purpose. I call it with 2 different names, test 1 and test 2, in order to visualize the differences. So now the test 2 is here, and I can see here in bright the presence of high value in the NBR. Similarly, for the post-fire event, okay, I'm gonna put it on top. Voila. So what I was expecting was very high value, and to high value meaning, okay, 0.38 for the very bright, and in the dark areas here, I got a value of around minus. So definitely, this is not a fire, this is vegetation, and the burnt area, it's negative. The ratio is negative. Okay, so similarly, we can build the NDVI or any other indices, like I think I have it there already. Yes, so this is the water index. It doesn't say that much. If, yeah, maybe in the vegetation we have a higher content of water compared to these drylands, agriculture, or maybe the NDVI. And with the DVI, of course, we have brighter values here in the vegetation. I can also apply a kind of palette color, something that shows bright values in green and the others bluish. Okay, so with just few clicks, now we have the original image, sentinel image. We have the NBR. Let's see. Okay, let's call the NBR. Okay, this is the NBR for time 2. So for the post-fire event. So now, how to proceed? One option can be just creating the difference of band 1 and band 2, or applying any other classification algorithm like the k-means, in order to see how we can improve our automatic classification of this area, of these burn scars. So okay, this is a raster editing. We can show you here in the tool. So what we can do is, in this case, is creating a difference between image 1, where we have no fire, and image, sorry, this is the test 2, okay, image 1 and image 2, in order to highlight all those differences. That's an option. But what I would like to say before proceeding in this direction, that is like the classical way of creating the difference between 2 images, like image 1, image 2, we create the difference. There is another way that is called disturbance detection, delta RNBR. This delta RNBR does the job for us. So it means that there is no need to compute individual image NBR and create the difference. The difference can be done using, for instance, the raster calculator. Raster calculator is like in GDAL or any other software. It takes image, for instance, I can do that directly in the tool. It takes image 1, that is your NBR time 1 here. Okay, image 2, okay, let's go quickly. Image 2, and then I do A minus B or B minus A. This is the simple expression that GDAL Calc uses in order to generate the output. In this way, we are creating an image difference with a lot of maybe false detections, because we have some difference, high differences in the vegetation and so on. But the trick here, when we are dealing about burnt areas or burnt areas issue, is using a tool that has been developed specifically for this purpose, that is called disturbance detector, just using the raw images in input. So we select the Sentinel-2 in time 1, so the pre-fire event, the Sentinel-2 in the post-fire event. I confirm. We select the bands that is generating the index. In this case, we don't care that much because it's the difference between two images. So it can be either both positive or positive in terms of the NDVI, or we can put it in the swap order, doesn't matter. And in this particular case, we are looking at every single pixel difference. So we are not trying to identify disturbances within the forest. This is the real objective of this tool. So in this particular case where we want to build the difference of two images, the raw difference of two images, we use the kernel equals 0. By running, I call it delta RNBR, by running this tool, we are able to obtain an image that shows the difference between the two. By double-clicking on the image, we can see the area of interest is this one. Okay, there is still an area here that is the result of the crash I had at the beginning of the presentation, but doesn't matter, forget about it. So the difference of the output of the delta NBR tool is exactly this option, this raster data, where we have very high values for the burnt areas. So a value of the delta of about 0.9, that means a very high difference, and almost very low value 0.05 where we are going into the soil or vegetation. So we see we don't notice any big difference between either the agriculture or the vegetation, because the difference in those 2 or one month is not so high. Sorry, just showing I just want to show the image. Okay, so here we go. So the difference in the vegetation or the agriculture is not even detected because they are quite close in time. So now I think we are seeing much better the extent of the fire, but still we have floating point data. We have 0.1, 0.2, and so on, so 9. So we don't have real classes actually. So what to do? We have several options actually. Options like automatic classification of this index. If we want to split or classify this floating point output into classes, we can use, of course, the automatic classification, not the automatic, but the k-means, for instance. Like, I want to take this delta NBR, and okay, I confirm I just need 10 classes, or we can even say 5 classes, and I put here class 5, and I push the run button. This is performing an automatic k-means classification or classification clustering into 5 different clusters in order to jump from floating point data to thematic. Okay, and this is the output. So we have like class, what do we have here? Class 1 and class 5. So we got something like a thematic output in an automatic way, but impact is done for also for raster and vector editing. And this is what I want to drive and what I want to carry you into the automatic vector editing and mapping of these burnt areas. So another option, as we said, as a preliminary step, is the raster recode. This is something that just few other applications are offering. So in case you want to perform some recoding of your raster data, you can right-click, start the editing, selecting the bands you want. In this case, we have only one, and performing like a kind of classification. So from 0.8 to 1, you can also visualize which is the area. And by doing that, you can recode yourself, having a preview of the burnt areas, just playing with thresholds. And if you want to be sure of performing a correct classification, I would suggest to have more ranges. More ranges means that you will be able to select, let's see if I have one slide somewhere. You will be able to select more classes later on. Yes, like in this slide. So what I have done, it's an automatic, it's a manual classification of the floating point input data, as you can see here, that goes from -1 to 1 into 10 classes, starting with a step of 0.1, from 0 to 0.1, 0.2, 0.3, 0.4, and so on. So the output of this recoding, it's visible then here. Stop the editing here. Now, when we show the info, like histograms or bands combination, we have a bunch of classes, in this case 10, with a dominant class that is class 1, that is the known, and the NBR close to 0, and so on. So with this editing tool, it's possible to recode the input data into classes according to the range you define. Interesting thing is the possibility of recoding only the current view. So imagine you are here on this area and you see that there is a mistake somewhere. You can select the range here. You can visualize what is happening, and you can recode the output only within the current view. So you are not affecting or recoding pixels that you don't see. Keep in mind this point, because that will be quite convenient where we are jumping to the vector editing mode. So the real land cover mapping activity. Okay, you can save in the file itself, or you can save on another file specifying the output file name. Now, we cover a little bit of data ingestion, clipping, raster classification, raster editing, raster recoding. manipulation of raster with the raster calculator with A minus B, or by using very complex formula to, for instance, calculate the emission factor per pixels and so on. So you can paste in very complex formula as well. So now it's time to jump on the real topic, that is the mapping of burned areas. And so why we built up all those indices? It's because I want to be supported by them, like automatic classification in several classes. Sorry, the automatic classification I've done with the automatic tool, maybe with the recoded classification of the delta R and the R, or with any other indices. I want to be supported in the image classification using the vector option. So image segmentation, zonal statistics, and then automatic polygon labeling and visual refinement. Visual refinement, this is something that we can then see. Another interesting step before opening the floor to questions is, and jumping to the image segmentation, is the bunch of data available, or the bunch of tools that are available also for changing data type, resolution, projections, available with the raster calculator. So in case you want to change the format from float, the data type from float to byte, it's enough to use the general tool, raster calculator, sorry, not the raster calculator, the raster conversion, that is this one. I just need to move the box one up. So the raster conversion allows you in changing. Okay, let me move a little bit away this one. Okay, in changing the format, like JPEG, if you want to put it on your paper, or reproject, or setting no data, rechanging the pixel size. This is nothing than GDAL translate or GDAL warp, in case also reprojection is involved, but with a graphical user interface handling in batch a bunch of inputs that you are providing. So this is quite convenient. Personally, I'm using Impact Toolbox to do all this kind of step. I was coming from a command line style, but I found the GUI quite convenient, and thanks to it, you don't care about the parameters, the syntax, and you can also use it in batch, especially in a Windows environment where batching this kind of processing is quite challenging. So before jumping to the vector editing, the vectors, the image segmentation, I would like to ask you if you have some questions regarding the raster processing. Okay, so if there are no questions, no raise hands. Okay. So why in this process of building a map of the extent of the burned areas, I prefer to work with polygons rather than pixels? Because with a pixel, we have a lot of noise. We can face the salt and pepper effect. We can have several pixels. For instance, if we see the delta R and the R, so we can clearly see that this bright area is the burned area. Yes, correct. But I have a lot of pixels all around, maybe related to correct burn areas. Let's see the image, and yeah, it's correct. So this is correct. This is a small field that is being burned. But okay, we have a lot of salt and pepper effects that we don't want to deal with. Also, when we count the amount of, when we sum the number of pixels at the end, we might overestimate the real extent of the burnt areas. So that's why the idea is to jump to image segmentations, to apply a processing algorithm that is able to aggregate pixels that are more or less similar and having, let's say, a color and compactness that we assign, to group them into one object. Then this raster is automatically converted to vector in order to obtain a segmentation. So a vector file that returns the extent or the area of pixels having more or less the same spectral properties. This is a tool developed by INPE, that is the Brazilian National Space Agency, and using the TerraLib libraries. This is an open source software, a bunch of libraries. I was collaborating with them in order to integrate these libraries, even the last release done at the beginning of the year in Impact Toolbox, in order to be able to use it in batch in another platform, maybe not common line. This core algorithm called BATS segmenter is the one that is available in the Fenians as well. So why mentioning that? Because as a big institutions, for instance, the university or the Joint Research Center or any other institutions can buy a license also for educational purposes with a huge discount, but still it's not free, it's not open source, and it's not portable. So you cannot share your license with anybody else unless you have multi-user license. So that's why in our capacity building objective, we thought within Impact, we must have a segmentation software that is free and open source. So running a segmentation is pretty much easy. As we see from the presentation, okay, it's enough to select the input data, eventually some classification to extract the information from directly in this phase, and some parameters. In this case, the band combination that we want to use, and some similarity and compactness. What does it mean? That especially the minimum mapping unit here is the size of the polygon that we are aiming at. So I think, yeah, I have prepared a slide showing all those information. So the idea is to ingest to take the input image, to perform some, to provide an optional raster layer where we are taking the majority that will be automatically taken and to fill the attribute table. For instance, in this case, we are taking the raster format belonging to the automatic classification we have executed at the beginning. So every single pixel, then a polygon, sorry, will contain an object ID, but also the majority of the underneath raster that is the automatic classification. Eventually, we can provide later on some extra attributes using the zonal statistics or whatever we want. So the minimum mapping unit is the key step for the segmentation, is the key parameter, actually. We see that if we need a kind of 50 minimum mapping unit, means 50 pixels as the minimum object we want to achieve, we want to get out from the segmentation, we more or less get this output. If we increase the value of the minimum mapping unit, we get larger and often heterogeneous objects. So it means that we have less chance to have pixel belonging to the same leg cover. For instance, in this example, this polygon here, sorry, this polygon takes a bit of agriculture, a bit of soil, and green, that is the gallery forest along the rivers and so on. So it's up to the user to test different parameters, different minimum mapping unit before starting this segmentation, before starting the mapping activity. Starting with the correct minimum mapping unit and thresholds, will ease the classification of our burn areas. Now, just to give you some live demonstration on how the minimum mapping unit is impacting into the segmentation. Here, I'm going to show the 50, that is a very low value. Like I just need 50 pixels minimum, maximum as the smaller object in the segmentation. And I'm going to overlay the 250, maybe with another color. Yes, here we go. So one big polygon from the 250 minimum mapping unit segmentation contains several polygons, several objects from a very fine scale segmentation. Okay, so this is just to show you how you can easily change the size and eventually perform an automatic or provide an automatic classification to the segmentation in order to have the attribute filled with the majority. As in the slide, now we can see that every single polygon here has an attribute corresponding to the automatic classification majority filter. So in this case, we got 11 that corresponds here to the most frequent class of this pixel, this polygon, in the automatic classification. So here we have all 11 that corresponds to this green class here. So it's quite convenient because now each polygon is or has a label in the T1 class automatically. What does it mean? That if we show, okay, I will go through the legend later on. If we show a classification, if we apply a color schema to our classification, to our segment, sorry, we can get some pre-labeled objects in one go. Okay, so it means that the majority filter has taken the raster data and put it into the vector DBF, the attribute table of our vector file. This is quite convenient because we have a kind of zonal statistics done on the fly. But if we don't have any raster at the beginning, or we are not sure about what to put as a thematic optional raster, we can build the zonal statistics later on. This tool, as any other GIS, will fill a new column in the attributes attribute table with the median, the mode, the standard deviation, the count, the percent, whatever you want, taken from an additional raster data. In this case, I did on the NBR, on the Delta NBR 10 classes spike. But okay, feel free to try in the tool. So we are now covering the image segmentation thema. Now it's time to put our hands on the classification or the creation of the land cover map using the vector data and pre-labeled objects. So before jumping to that slide, if you have some questions, please go ahead. Okay, so in the last minutes before giving the floor to the final interactions and questions, I would like to cover the aspect of the real, actually, land cover mapping thema. First of all, defining legends, because the key step is the definition of the legend. In Impact, it's quite easy. There is a module. There are some default legends like land cover or the standard 50 classes, but also the current land cover classification legend that is used in the Sardinia project, in the Sardinia land cover mapping project, containing up to the level 3 of Corinne. In case those legends are not enough, you can always apply and build your own legend by using a dedicated, let's say, tab option of the tool, where you can define your legends, such as like zero no data, vegetation, soil, and burn. This is quite easy and convenient just by showing the vector legend. Here we go. We have different legend. You can apply ID, name, like a description, and color. Corinne is a little bit more complex. It has classes, key classes, and subclasses up to level 3. But in our case, I want to, let's say, use the default color combination, color legend, with no name and classes because, okay, I want to keep it simple. But for this purpose, I also did a test on my legend. So it's enough to edit, for instance. You can change the burn area, you can change the color. Here you can put it in red, and this is how to define the legend. But okay, doesn't matter. Let's jump to here, the vector editing. So we are very, very close to the creation of the burned areas map. In order to start the mapping activity, we have to assign, as I said before, a legend to our vector data, our vector file. And in our case, I just select the 050 legend, the 050 legend and colors used and available in Impact as default. The color combination corresponds to the automatic classification. So that's why it's already available in Impact. So it means that class 10, it's visualized as green, 10, 11 that we have seen before here, that corresponds to the vegetation, while the red and pinkish are belonging to the soil and also dark soil in violet. So in order to be more, let's say, in line with the default settings, so we don't want to change too much in this presentation, the Impact Toolbox, I'm using this vector legend. So once we have it, so we can navigate and see that, as we noticed from the automatic classification, we got some classes, but not all of them are correct. For instance, when I zoom out, I can see that there is a confusion between the water class and the pink class, that is what we suppose is the burned area. So now we jump into the vector editing mode. So what we can do either visually or automatically. Now I'm going to cover both of them in a similar way, without giving too much, let's say, strength or too much weight on the fully automatic or the visual interpretation, but we can improve the quality of the input map, the input pre-labeling, using automatic processing. So as I said, the mapping requires the assignment of a legend to our vector file. In this case, we use the 050. There is a match between the attribute table within the T1 class and the color in the map, what you see. And now it's time to start the editing. Starting the editing of a vector file, it's pretty much easy. You just right-click on the file, click on the Start Editing button, and an interface showing the different options is appearing on top of your map. The interface is divided in selecting what to save and where to save, and what to save. So the output class, including a legend that is appearing automatically collapsing in order to free a little bit of space on your map. So with this tool, we can either select by point, so point and ID. It means that every time you click on a feature, you get this feature by itself alone, or by pushing the control, click several features. You can also select by classes or by attributes, any other attributes in the map. So I don't want to go through all those options because they are documented in this presentation, in this slide. I just want to show you live how easy it is. So as I said, start editing. This interface is appearing. We can collapse, we can squeeze all the unnecessary tabs, panels in order to maximize the map view. And so what I've noticed is a mistake here in the classification. So if I click by polygon, I can select one single polygon per time or multiple polygon by pressing the control, or what I can do is to select by class. Selecting by class, it's giving me all polygons with this class. The class is here, it's 41. I don't think you can see it clearly from the presentation, but what I've clicked is a class called 41 in our legend. The legend is here, and 41 corresponds to the dark pink or the violet class. So if I recode with a right click into water, I will recode everything, including all those polygons in the burnt areas. So here comes what I mentioned already before, that is recode only those pixels, but within the current view. So now if I zoom on this area, I'm gonna recode everything that stays in this window as water. I can assign the class blue. And as soon as I move a little bit the map, I can see several other polygons popping up, including the mistake coming from the automatic classification. Okay, so as a first suggestion, I propose to okay, here we go. Editing tool here. So the first suggestion is recode only what you see. So if you don't see polygons because they are outside the map extent, the common mistake is to keep recoding objects from one class to another without being sure of what you are doing, because you don't see the actual amount of polygons. So the vector editing tool, first step, select an area. Second, recode evident mistake first. So if there is a class that in water is not correct, just go and recode it. So again, okay, I'm gonna recode quickly also this part. I just moved the image, the map there, right click, and I'll recode to water. Now, when I go back to my map extent, I already have, okay, a classification that it's more or less okay, but still a lot of polygons are missing. So now the key option is to use auxiliary data like the NBR index to classify this image, to classify all those polygons. And don't forget that we have done also a classification in 10 or 5 or whatever classes using the delta R NBR. So if we use the zonal statistics to fill the shapefile, the attributes table using the NBR, we can already have this information within the shapefile. So if I open the file using the same legend again, visualizing here, the attribute, the legend with as before 050, and starting the editing, I can show you in the attribute table here that with the zonal statistics, I have now an attribute that corresponds to the mode, so the most frequent value of the 10 NBR classes that we have done with the raster editing. So what does it mean? That I can use these attributes either to select the bunch of pixels or polygons in this case I want to reclassify. So if I go into the T1 cluster, that is the place where, sorry, the T1 mode, when I click on one attribute here, okay, I can select information coming from the NBR 10 classes. Okay, so this is just to show, and you can follow more in details in the slide. You can use this option in the attribute table coming from different sources in order to classify polygons using ancillary data, extra informations. So this is very, very convenient. So now just to see which is the impact of the selection of the class 5 from the delta R and BR, I want to recode it on purpose into another class that is this light blue. And I just hide the classification, clear the selection, and stop the automatic classification, stop the editing. Okay, so now the recording is, okay, it's happening. Here we go. And I have recoded everything that comes from class 5 from the delta R and BR automatic clustering into another class in order to show you how we can interact with the DBF attributes and the classification. So the message is rely on any kind of material you have in order to be able to classify your objects. So you can use, in this case, the NDR, you can use the automatic classification, you can use NDVI if you are looking at the vegetation, NDWI for water, and so on. So those are all objects that are or tricks that are speeding up the classification. There is another interesting feature that is in Impact when doing the editing is to enable or disable some classes in order to visualize omission and commission error. So by switching or by keeping only the forest class on, the burnt areas class on, you can see all the forest underneath, you can see the agriculture, the bare soil, but you can see also some holes corresponding to a burned surface. So with the omission error, you can highlight polygons that are not classified as burned, and vice versa, visualizing all classes but the burned one, that is the first one, you can see the commission error. So you can see if you have some pixels or polygons left in the burned areas, maybe corresponding to dark soil but not burned, or vegetation. Okay, but okay, yeah, in the workflow, we have used the delta NBR as a way of highlighting all these burned areas in order to automatically classify our polygons. But what you can see here, it's a missing classification of this area. What's happened? So if we zoom to the entire section, okay, now this is classified because I did it for the presentation, but if we jump into the image, and in order to show the two images, okay, here we go. This is image at time 2, and this is image at time 1. Here we go. So you see, this area is still there at the beginning of our observations. So at time 1, 5th of July. That means that when we build the delta NBR, that is the difference between the two images, this area is not detected as a change, or maybe as a slight change, because it's a difference, so that there is no much difference in the two. So what we can do, we can use the individual image or individual NBR in order to facilitate the selection of objects, polygons, in this area, or you can also use a manual object selection if the area is small and confined. So by clicking on few polygons, few objects, we can assign the classification by hand. So the next step is to get some statistics out of our final classification. This is the vector, the classified vector data. I've changed the values on purpose there. I also, in my editing mode, I also assign different classes to the burned areas, including some partially burned. This can help in the maybe emission or biomass loss or emission factor computations and so on. So you are free to edit the legend to include any kind of information you might need for the estimation of the emission or biomass or the extent of your burned areas. Okay, here we go. So I did this manual processing of Sentinel data up to the classification, segmentation, and not validation, but yeah, visual inspection and recoding in about 1 hour. So to do what? To then extract some statistics. Okay, so the statistics means, okay, you can build it from the raster data, from raster data. So once you have your vector, you can convert to raster, setting 10-meter resolution as the pixel size, and to get a burned, not a burned area with a sum of, yeah, it's 137 or 13,000 pixels. Similarly, you can build statistics in any other software, ArcMap, QGIS, or Impact as well, getting the real estimate, maybe converting to equal area or whatever you want in terms of hectare using polygons. What we have seen at the beginning, I showed some press, some news titles saying over 20,000 hectares devastated. Actually, the size of the burned areas detected in this exercise, it's limited to 30,000. Am I correct? I would say yes for this area, because I can clearly see that the classification, it's pretty much in line what I can see from Sentinel. But honestly, I think that the extent provided by the media, it's also related to a wider area that is maybe including also this southern fire and maybe some other smaller fire. But still, there are 7,000 hectares missing from this classification. So again, this is an example of how to prove in an hour or so if the information we got from the media is correct or not. This is an exercise we have done for Brazil, we have done in the tropics, because, okay, the media somehow are, I don't say always correct, but they want to impress people, okay? But us as a scientific expert, we are supposed to provide evidences. And I think this is a good way of doing that in an hour or so. Okay, I'm jumping to the end. Saying that what you can do also in Impact, but as in any other GIS, once you have your map, burned, not burned, you can intersect